Welcome to Biomechanics on Our Minds. My name is Melissa Boswell.
And I'm Hannah O'Day, and we're PhD students at Stanford University.
This podcast is brought to you by the International Society of Biomechanics.
It's
time for Boom.
Welcome to Boom, where we have
Biomechanics on our minds.
Boom.
Boom.
Boom, boom, boom.
Boom, 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 boom.
Boom.
Welcome to episode 39 of Biomechanics on Our Minds. I'm Melissa.
And I'm Hannah.
And we are
today...
recording on Hannah's birthday. Happy birthday, Hannah. Sorry, that wasn't in the script.
You didn't write that down.
Everyone message Hannah happy belated birthday because this is obviously coming out after and she needs to remember that or be celebrated still 1 month after her birthday.
Thank you in advance. That I didn't know Melissa was going to do that. I didn't ask for that. I do not endorse this. Anyway, you all should be celebrating because you have an awesome episode ahead of you. Today we talked with Professor Glen Lichtwark, who is in the School of Human Movement Studies at the University of Queensland. So it was an early morning for him and a nice afternoon chat for us. And he's also a member of the ISB Council and a collaborator on a project with our lab. So it's been really exciting to get to know him and talk to him more.
Yeah, it was fun to have a few members from his team come over from Australia to work on a project together and get to know Glen better that way. And we're excited to have him on. And he talks about some really fascinating topics like the relationship between basic science and translational research. He shares his early explorations in biomechanics that was inspired by human and animal movement, and some recent exciting research on the muscles of the feet and importance of the arches.
The arches.
The arches.
If we were in Boston, that's how you.
Yeah, I was like, I don't think I said it like that, but Hannah's bringing out her Boston accent. But before we get started, I have a bit of boom to share.
Bit of boom. Bit of boom. Bit of boom. Bit of boom.
Well, this is recording. We just had the Super Bowl yesterday. I'm bringing a little American football biomechanics, some footy football.
Football is American.
Yes, American football. So every time we're saying football from here on out, we're referring to the American football. So in football, it is very well known and unfortunate that concussions are a major problem due to the constant impacts between players, which we saw a lot of yesterday. And it just always makes me cringe a lot and feel stressed out. And this can also lead to neurodegenerative diseases like chronic traumatic encephalopathy or CTE. And a recent study actually investigated the effect of player position on the risk of CTE. So what position a football player plays, how does that affect their risk for one of these neurodegenerative diseases, likely due to the types of impacts that they have? So there's a study published in the March 2021 issue of the Journal of Biomechanics by Carl Zimmerman and colleagues at the Empirical College of London. And they use computational modeling to test whether player position has an effect on brain deformation within the sulci, which is a possible biomechanical trigger for CTE. And if I'm remembering my brain anatomy, the sulci are the grooves in the cortex, and then the gyri are the bumps or the folds. Mm-hmm. And it was pretty neat. They actually reconstructed 148 head impact events from video footage of football games.
Wow.
And they found that the positions that players were exposed to large magnitudes and low frequency impacts. So like the defensive back and wide receiver positions, the strain and strain rate across the brain and in the sulci were the highest in those positions. Also, they found that the rotational head motion is a key determinant in producing large strains and strain rates in the sulci. Overall, they found that the player position does, in fact, influence how the brain and sulci are deformed, which spatially corresponds to where CTE is observed.
So you're saying if you're playing in those positions and you're getting a lot of rotational motion, your head's twisting a bunch as you're getting tackled, those are the worst things for you.
Yeah, exactly. It can be really helpful in then assessing concussion risk and maybe then designing position-specific helmets or other protective gear. And I think it was also just a really cool design in recreating these impacts from video. And I could see it being really useful in other situations and other impact sports, and also maybe car crashes or falls and things like that. And actually one of those reels of someone attempting parkour but failing and like falling on their head was popped up on my feed today, and I hate watching those videos, but I was like, oh, it could be interesting to recreate those and see the types of traumas that might be occurring. But yeah, I thought this was a super interesting study and important to like think about how these impacts are differing across the different positions people are playing, and how you can do a better job at understanding that and take precautions against that.
Yeah, and that's also super useful. Like I know there's some research on different tackle strategies, or like could we just shift a little some of the motions that are happening to be a little bit safer and not lead to these sort of dramatic and drastic impacts for these players. And I think this analysis is key in moving toward those steps to changing those impacts.
Yeah, definitely. And then maybe I won't feel as upset watching football games.
Yeah, it is a lot.
All right. Well, we're excited to shift into our interview with Glen. We're really excited to be talking with Professor Glen Lichtwark. Glen is a professor in the School of Human Movement Studies at the University of Queensland and is a member of the ISB Council. And he's also been a collaborator on a project that we've been working on measuring fascicle and sarcomere length adaptations in response to eccentric training. So it was really fun to be able to work with you on a project. And we're super excited to chat today. So thank you for being with us.
Thanks, Melissa. Thank you. Thanks, Hannah, too.
We're super excited to talk to you. And we always love this question. We like to ask, like, before we get into all of your research, we'd like you to share with us what first got you interested in biomechanics.
I was always a bit of a science nerd through school and high school, and I was particularly interested in the human body. So if I think back to some of the little science projects that I did through high school, there was everything from separating plasma from blood to looking at what different types of sugars are in sport drinks to heart rate and exercise. In senior high school in physical education, we did a unit on biomechanics, and that's kind of when I first decided that I'd like to pursue something in that area. And so I did a degree here at the University of Queensland, where I'm now working in human movements and mathematics, and really just took part in as many opportunities to do research as an undergraduate, including working in the GATE lab over at summer and doing various research projects. But then in my final year as an undergraduate, I actually did an elective course run by Professor Mike Bennett on animal mechanics. And this really changed how I thought about biomechanics and what biomechanics could be, because I'd always thought about it about just being humans. And when I decided I wanted to go traveling abroad, I thought that actually animal mechanics might be something cool to do for a while. Yeah. And so I moved to the United Kingdom, and I did a cold call email to work to Professor Alan Wilson, who was at the Royal Veterinary College, and they just published a cool paper in Nature around horse limb biomechanics and muscles in horses.
Wow.
He somehow said yes to come and work with him. So I worked with him for a year and then ended up getting a scholarship to do my PhD with him. So I did a little bit of work working with horses for a year, and then actually moved back to doing human stuff for my PhD.
What was that transition like? I'm wondering, like, you went from human to animal and then back to human. Like, what motivated?
It was really easy, I think, because we were interested in the same ideas, right? It was, and this is, and I guess I'll talk a little bit about it at some stage through this podcast, but we were interested in relationship between muscle structure and its function, and horses are just an extreme athlete, and we're interested in how these extreme athletes work and how they power movement, and that was the same theme that moved into my PhD when I started looking at humans.
That's very cool. I feel like we had a guest on before that talked about a race, like the human versus horse race that they have. And I don't know, it just reminded me of that. And when you said like they're these super athletes, yeah, it's pretty amazing what they can do.
It is, yeah. And I actually grew up on a horse stud, so I had an interest in horses anyway. So and I know they're powerful. I've been run over by horses numerous times, so they certainly are powerful. Yeah.
Could you outrun them?
No. I briefly, for a brief period, yeah, for like the first 10 or 15 meters I can, but I'm not that fast now.
Yeah.
You got to go for endurance.
Yeah, that's right. Yeah,
Exactly.
Yeah, go for endurance.
Yeah, so fast forwarding to now, we would love to learn more about what research you're currently working on. On your Twitter page, I really like that it says you're interested in muscle and tendon mechanics, locomotion, modeling and simulation, robotics, and then all things nerdy. So we would love if you could tell us more about these nerdy things that you're working on.
Yeah, sure. I mean, a lot of what I do is really what I would classify as basic science. We're trying to understand how different muscles have evolved and why they have, and how they've evolved in particular with the nervous system in the brain, which can obviously controls our muscles, to allow us to perform movement that's economical or powerful or even precise sometimes, because we have to perform a variety of tasks. And that obviously has applications in lots of different areas, ranging from exercise science to robotics, because in robotics you want to be able to design a robot which is diverse, whereas in an athlete you want to be able to maximize performance in some way.
Mm-hmm.
So I think what we do is really trying to do basic science most of the time, but it does have direct application. So the sort of things that we do is we like to try and firstly make measurements of muscle structure and function. But really I think what separates our work, or has separated our work from a lot of other people, is that we really like to look at dynamic muscle function. So we do imaging experiments with ultrasound or other imaging techniques during real movement tasks, walking, running, jumping, whatever it might be, and use design experiments and also simulations that really try to perturb the natural system so that we can better understand why it is that we move the way we do, and really try and discover the fundamental aspects which let us achieve the things that we can achieve. This involves everything from doing experiments on isolated animal preparations from different animals, doing measurements on intact muscles in humans, looking at just single joint motions, and then doing whole body measurements in the lab. So sometimes also doing measurements in the field using wearable sensors and other things. And then, of course, based on all that research, there's always side projects going on, and a lot of those side projects are much more translational, looking at things like muscle development in children with cerebral palsy, or how muscles adapt to training or disease.
Yeah, that's so interesting. And it's interesting to see this different scope, or I guess the difference between like more basic research and then more like clinical or translational research. And I'm curious if you could also just touch on maybe how they inform each other in your work, and how the insights that you gain from basic research or basic science research can inform more of the translational research.
Yeah, I mean, it goes both ways actually. Occasionally the translational research informs the basic research as well. So on the first part, we've been measuring things like how the calf muscles, fascicles interact with the tendon to store and return energy during locomotion, and what contribution this makes to our economical movement. But of course, this sometimes breaks down. And so an example would be in cerebral palsy, where we have children who have contracture, and there's long-standing beliefs just because of how people have thought about things, about how muscles are shorter or weaker, etc. But a lot of those things were never really tested. And so the benefits of the sort of techniques we were using in basic science were that we could then directly have a look at movement function and how the muscle is made up, the forces that it experiences, the length changes that the fibers experience, how much energy is stored and returned in tendons. From that, we can actually start to get a better picture of what it is that's causing things like muscle contracture in a child with cerebral palsy. But alternatively, sometimes when we start thinking about translational research, so we've done a lot of research as well into foot mechanics in our lab, and particularly led by Luke Kelly, who's a postdoc in our lab, junior scientist. His research was very much around the function of muscles in the feet, but it also took on an element of how the feet interact with things like footwear. And even in just thinking about some of those relationships between how the foot interacts with footwear, we can then take that back to basic science and think about how do those different factors, like how stiff the shoe is or the bending stiffness of the shoe, how do they actually influence whole body mechanics? Because that's actually a fundamental question in science.
I love hearing you talk about and explain these sort of like the symbiosis, right, between these different sides and perspectives. And it's nice that your lab's able to integrate and collaborate to make all of those different avenues possible. And just thinking about that integration, I'm wondering if there's anything that you have learned from your research that you've been able to integrate or apply to your daily life, or that you feel has changed your personal perspective or outlook on life. This can be something very small, like some finding that maybe affected how you think about something, or sort of a larger scale type thing.
One of the beauties of biomechanics is that you can sort of see it in everyday life and feel it. But actually, and from teaching biomechanics to undergraduate for a long time, I've sort of realized that you actually don't really need to have a strong understanding of biomechanics to implement biomechanics in a sensible way. So an example I use in my undergraduate courses would be that someone training for Ninja Warrior, they know that when they make a landing that they need to extend their arms over a long period of time. They don't know necessarily that the mechanistic reasons for that they're trying to absorb energy over a long period of time, or so that they can reduce the forces that their arms need to experience. They don't know that, but they've worked it out, right? That's one of the beauty of biomechanics. And that's actually one thing that I love to study is how is it that we just know that, right? Well, we can do it from experience, but also there are some intrinsic things, the way our muscles work, that help us to be able to do these things inherently. So, yeah, there are fun things about biomechanics that we can teach. But for daily life, I think, I've worked with a lot of researchers who study children with cerebral palsy, which I mentioned earlier. And in this population, you quite often see that parents and children quite often, they're desperate to be able to walk what they consider to be normal, or much more like a typically developed child. And that drives a lot of the motivations behind some of the clinical decisions. And that's not necessarily a bad thing. But the more that I've looked at these sort of problems, the more I sort of worry that treatments like surgery or Botox, while they might have some short-term effects in making children look like they walk more normally, they might actually have more detrimental long-term effects, and that sometimes we've overlooked some of the adaptations that occur, which might actually be occurring just to enable function in the longer term. We have so many degrees of freedom in our body that if one part of the body isn't doing something, we can switch to doing another thing, and there's going to be adaptations. And I think my perspective on how we perform interventions has changed a little bit in that way over time, that there is not necessarily a normal way of doing anything, that whether that be somebody with a disease walking or an athlete trying to do something. There's just so many degrees of freedom that we can find an optimum way of doing things. And that's, I think, one thing that personal perspective that I've developed over time.
Yeah, that's such an interesting point. It reminds me of so many sports like figure skating or gymnastics, where you're spinning and, you just kind of bring your arms in, and it's just these things that we do kind of naturally, or you're falling and your arm's going to go out. But thinking about actually the science behind that and why we do that is fascinating. That was a really interesting point. Yeah. So recently your group published a paper called The Functional Importance of Human Foot Muscles for Bipedal Locomotion. From previous work, it was the expectation that the intrinsic foot muscles contribute to supporting the arch of the foot during walking and running. But then you found that to not be the case, and instead included that the muscles influence our ability to produce forward propulsion. And I'm curious what you think is most exciting about these findings, and how the findings might impact how we think about the function of the muscles in the feet.
Firstly, it was a pretty cool study to be involved in, and a lot of the credit has to go to Luke Kelly, who I mentioned earlier, and also Andy Creswell, who I work with closely here. He's former ISB president. I actually met Luke at an ISB conference in South Africa.
Oh, that's great.
When he
in
was
Cape
at the
Town,
time
probably.
Yeah, that's right. He was working as a podiatrist in Qatar, although he's from Australia. So he actually started a conversation with Andy Creswell around doing electromyographic measures of the muscles in the feet, but the detail, or the difficulty in doing that is you have to use fine wires, so you have to stick needles into the feet. And so they were doing this, and when I became involved in the project, they were really interested. I was asking the questions of what do you think these muscles actually do? So we started designing experiments around what they do, and that led to this hypothesis that maybe they help support the arch of the foot. But you have to be a little bit pessimistic around these hypotheses sometimes, because you say, well, some things, this whole correlation causation thing, you turn these muscles on and you see a response, but we don't really necessarily see. It's very difficult to make a definitive statement as to this is what these muscles do, because we know that forces generate changes in energy, and that energy can sort of go anywhere in the system. So we wrote a grant to sort of determine whether or not we get this tunability of the foot or the stiffness of the arch of the foot through activation of these muscles. And the only really way to determine whether or not they were having this function was to take the muscles away. That was the cool part about this experiment. We were lucky that Luke is a podiatrist, and therefore is registered and licensed to be able to do nerve blocks. And so we do nerve blocks on the feet, and we get people to run with and without the nerve block. And the nerve block basically stops all incoming drive to the motor units to the foot. It also means that you can't feel your feet. So when you're running along and it feels like you're running on stumps a little bit. But you're perfectly able to run, no problems at all. We actually found that our original hypothesis wasn't necessarily true, that the arch of the foot deforms in a similar way, experiencing very similar sorts of forces, which I guess was kind of a view that's been held for a long time, that it's really driven by the stiffness of the plantar fascia, which sits at the bottom of the foot. But we did see fairly drastic shifts in the energetic function of the foot, and that in particular, we see that, as you said earlier, that there was less energy stored and returned within the foot, and particularly we've continued on that research, and it's fairly clear now that the muscles are really important for contributing energy at the forefoot, and particularly around the toes, and how those contribute energy. And so if you take those muscles away, you can still run, because there's, as I said earlier, there's many degrees of freedom. And so typically what happens is there's less power being generated at the foot, but then that power just gets generated somewhere else, usually at the knee or the hip. And so from an evolutionary perspective, this was actually quite important, because it tells us something a little bit about why these muscles have developed the way they are in conjunction with the arch of the foot. And it's a little bit different than the size and the structure of these muscles is different than other both extinct and extant hominins. So.
Wow. That's so cool that you can look with these experiments get a look into the past a little bit. The nerve block experiment is like a really nice way to get like specificity and like really look closer at the mechanisms that are at play here. And I'm wondering if, as you were kind of mentioning earlier, like you're wondering about what is instinct, what is intuitive about our biomechanics. Was there any subject feedback on that might have matched some of the intuition that the subjects were having, that might have matched what you were finding scientifically or biomechanically?
As is the case with a lot of these experiments, I'm usually the first participant, so I can give you my own personal.
I really appreciate that about you, Glenn. I feel like whenever, even in our study, you're like, well, let's just test it out. I'll sit on the table and, I'll be the first subject.
You can stick needles in me.
Yeah.
Yeah. I've developed a pretty high pain threshold now. It's a weird feeling, right? And that's actually a limitation of the approach of a nerve block, is that you take away also some of the sensory aspects of the foot, which might actually have their own feedback mechanisms, which might drive things like the ankle function, which also changes when we induce these nerve blocks. So I think when you do run it, it feels funny and it feels weird, but you can easily find a way. You've got the right motor patterns, they're already there. I don't think you consciously know what it is that you're doing when these things are taken away. It's just something that happens. While you might think, I vaguely remember feeling like I was using my hips more, particularly during the swing phase. I felt like I was using my hips a lot more, but I don't think I could physically describe exactly what it was that made me feel like they were doing more. It was just something that was happening.
Wild.
That's so interesting. And I'm thinking back to when you're talking about using the fine wire electromyography to study muscle activity. And I'm curious with that, if you want to look at, so with a nerve block, assuming then you weren't able to control any of the muscles in your feet, but if you have the fine wire EMG, you can maybe target like individual or specific muscles. Is there a way that you do that? I don't know, with ultrasound or something to help be able to make it more specific?
We've used direct muscle stimulation, so we've gone the other way. So rather than taking the muscles away, we've added stimulation, not during walking and running. It becomes a little bit hard when you do that, but we've done it during loading experiments. That's how we came up with the initial hypothesis that perhaps these muscles help support the arch of the foot. It was a fairly large study, the one that was published in that PNAS paper. But we do find that you can control the arch of the foot, or you can control the height of the arch of the foot with these muscles at relatively low forces, so within body weight range or just under body weight. So if you put some load on the body or on the legs somehow, and then you stimulate the muscles, then you do see deformation and changes of the arch as the arch height rises. But it's just that when we go to something like running, the forces are just so much higher, and that point of application in the force is so much more anterior or closer to the toes, and so we have much bigger moments occurring around the midfoot, and this is basically means that the size of the force that can be generated by these muscles isn't sufficient to be able to necessarily control the shape of the arch of the foot. But it does, however, contribute to forces at the MTP where the moment arm's a lot smaller. And I think we have used ultrasound on these muscles, and they are very similar to the sorts of muscles that I've studied a lot in my life, with short fibers and relatively long tendons. And so they not only can contribute to energy within the foot by producing relatively high forces for their volume because they have short fibers, they also store and return elastic energy, which is the key aspect, I think, for these muscles.
Well, you had another, speaking of arches, I feel like you had another paper. It was a Nature review entitled Ahead of the Curve in the Evolution of Human Feet, where you describe research on the role of the transverse and longitudinal arches of the feet, which I didn't actually know technically where those were. But so the transverse is at the front and then longitudinal is along the side. That's sort of the traditional arch that I would think of. And so you highlight an analogy that helps explain why the transverse arch's curvature might help prevent this foot bending and therefore increase foot stiffness, which I really loved and appreciated this analogy. So I'm going to quote it here. You said, it's like the way that a pizza slice becomes less floppy if the slice's outer crust is curled up. So this is just a really great analogy. And I love that the article was very accessible, and this analogy is very accessible to anyone wanting to sort of learn more about this. So we're just wondering if you could tell us a little more about the mechanism and maybe how you kind of came up with the analogy and how all of this plays into the human evolution story.
Well, I'll start with how I came up with the analogy, because actually I didn't come up with the analogy.
Oh, sorry, you're right. It's in the paper. I'm sorry.
Yeah, well, no, So I mean, they use a different analogy. I'll give you the background. So obviously, that's one of the best parts about being an academic is you get to read and review lots of great research. And so I was asked to write a commentary on the research, which was done by Madhu Venkatasan and a whole lot of other colleagues. And it was a really novel piece of research around this new hypothesis, or at least the first time that this hypothesis has been really tested around how the transverse arch might actually make the longitudinal function of or longitudinal stiffness of the foot more stiff, which is a really important thing for applying force to the ground. We don't want to have too floppy a foot, otherwise forces can't be transmitted and we can't generate power. And so I'd actually spoken to one of Madhu's students who was also a key author on this paper, Ali Yawar, I think his name is. It was actually at the ISB conference in Calgary, and it was not long before I got asked to write this commentary. He actually gave the analogy to me of the pizza, and that's different to the analogy they use in their paper. In their paper, they use the analogy, I think it's if you curl a currency bill, like a dollar bill, pound bill, or a euro bill, whatever it is, whatever currency you're in, try and keep it as international as possible. If you curl those and you push down, then it's quite stiff. If you let it flat, it's not. So, of course, after I heard this analogy of the pizza at the conference, we of course went out and had pizza that night, and I tested the hypothesis, and it seemed true. So and that was enough for me. I was sold.
That's very scientific, and it also very I feel like that's much more relatable for us as grad students. An analogy towards pizza versus one with money. So really appreciate you coming to speaking to us.
Very inclusive.
It's a really neat sort of mechanism that they explore with this, and they use some really interesting analyses of how particularly extinct hominin species have a different curvature of that arch and how that might influence the stiffness of the foot and therefore their ability to walk bipedally. That's the key message from this. But, to get into nature, you have to do something pretty special, right? And so they have it was a massive project. They had physical models, they had mathematical models, and then they tested cadaveric feet as well. And although there's still a lot of research to be done to see whether or not that is directly transferable, or we can, for instance, try and modify the transverse arch of the foot to stiffen a human foot for surgeries, for instance. There's still a lot of research to go about that. It's a cool mechanism, and it's nice to be able to make a commentary on those types of research when given the opportunity.
It's cool too, because I think also, like, as the authors, it seems like it also brings more attention to the article, or just, different way of understanding their work too, which is really interesting.
Those sort of commentaries are a different sort of narrative too. The brief, you actually have a brief from the publisher in this case, which is, please write something which is accessible to people and that people might be able to understand, and focus on what the potential implications of that research or how that might be translated. And so it's nice to be able to do that without actually having to do the research. I mean, I can't imagine.
Doesn't get much better.
I can't imagine how much research their team had gone through to do that. As I say, it was a massive piece of research, but it's nice to be able to do those things sometimes.
Yeah, and I'm curious too, as you were talking about changing the transverse arch with surgery, are there any other mechanisms to change some of these things that you're talking about in terms of like the floppiness of the foot or the shape of the arches and things like that?
I think there would be certainly people who might think that you can use an external support, like a orthotic type approach, to maybe try and manipulate curvature of the transverse arch. Probably a little bit hard. A lot of it's intrinsic, right? And so it's like just how the foot's developed. Some people are going to have fairly high curvature. So curvature is different than the height of the arch. It's like the actual curvature from the front. So I guess what we don't really know now is what the real variability is of that curvature across the human species, and whether or not we have people who might cross into different hominid species or the great apes or whatever, and whether there's a crossover there which might be directly related to the stiffness of the foot. But of course, there are other mechanisms. We've been investigating the role of the intrinsic muscles. There's also the extrinsic muscles. There's many different factors which might contribute to how stiff a foot is or not.
So instead of like ancestry.com, we can maybe just look at people's foot stiffnesses.
Foot stiffness, yeah. That's it, yeah.
Yeah, it also makes me think about how it's developed based on our environment too, and the shoes we wear and the types of activities we do. And so it's really interesting. And we also noticed that in the paper you state in competing interests that you have an ongoing funding with Asics Oceania. We were wondering if you could just elaborate on that collaboration or how that funding works, and then what it's like to build and kind of sustain this relationship with a company in industry.
Yeah, sure. Well, in our lab, we have a few different industry partners, but Asics Oceania, which is just the Australasian branch of Asics, it's a Japanese company. But this collaboration really started through my colleagues, Andy Creswell and Luke Kelly, partly because of, Luke was a podiatrist, and so already had a working relationship with numerous shoe companies, but also the company itself was a key sponsor of Sports Medicine Australia and their conference every year. And so, these are people who wanted to support science in particular. And so they were always open to talking about science and potentially funding that. And they funded a lot of science across Australia. And I think we were doing really basic science, but they were happy to see the potential of where that might go. And I think Luke, along with Dominic Farris, who was a postdoc in our lab, and Andy, have really sort of developed this nice partnership around what we do, where we still do relatively basic science to try and understand how different factors which might be incorporated into a shoe might affect foot function. But they've been really open partner in being able to sort of listen to our ideas and then work with them around those ideas. And that's different to some other partnerships we've had in the past, where things are very much more prescriptive, I guess, and there's very specific key performance indicators and milestones that you have to meet along the way. So I've done projects with like Cricket Australia, for instance, where we've had very specific milestones to meet. And in those instances, communication is the most important thing to maintain in a relationship, because things will inevitably go wrong, or sometimes there has to be a change in tact, and you have to be on the ball all the time to communicate those things. And so those sort of relationships can be really rewarding, but also really challenging.
I can imagine. And just, it's almost like when you I feel like our advisor is often hands off. And so if you lose communication for too long, it's like you gotta come back and
I would actually
fill
say
in
that
that gap.
I would say that I've had some relationships with different outside bodies at different times where,
Mhm.
it has just fallen off because you don't take the initiative to make sure that they're informed. And it's a real shame when that happens and you look back on it and you think, oh man, that was a real opportunity lost. And so that communication is really important. It's the same with working with anybody though, right? Any collaboration, the communication is important. When people are busy, not just academics, but on the industry partners as well, you have to recognize that they also have competing interests as well. And most of those are financially governed. So it's important to be able to try and meet those obligations where you can, but also try and build on those relationships and make sure that the next thing that you're thinking about is something they might also be interested in.
Yeah, that's true. It also makes me think of the differences in terms of like expectations and like timelines between industry and academics. Like I feel like in academics sometimes like pretty soon is like in 6 months to a year or so. And in industry, like pretty soon is like this week or next,
That's right. Yeah. And it can have financial consequences, so that's one of the problems. I think our relationship with Asics though is primarily down to Luke Kelly for trying to foster is that if you can get some of those relationships where they're happy just to see the really good science being done and they can cash in, they will. But if not, they're happy around that because because they feel like they've done something good for the world, then they're the best ones.
The philanthropic.
Yeah.
So we're actually going to switch gears a little bit. Thanks for sharing all those great experiences with us. And we're going to ask if there's ever a time in your career that you felt like you have failed and what did you learn from that experience?
Am I allowed to say failure is not an option? No.
Yeah, but only if you follow it up with the time that you messed up.
Yeah, I mess up all the time. And, I hear you ask this question all the time on Boom, and most people say the same thing, is that the best thing about having a failure is that usually it leads to something new and interesting to look at. But I could list lots of failures. I've got studies that I've done in both my PhD and in my postdoc that they've been fully written up, but they've been shelved, partly because there was something that wasn't quite right. I didn't quite have the right support, and that's fine because you learn from those. But I think when I started my PhD in the early 2000s, we were using ultrasound to measure muscle fiber length changes during tasks like walking and running. And, at the time we were going through frame by frame, measuring the length of fibers or multiple fibers in the image, moving to the next frame, and it would just take forever to do, right? And so, I was young and enthusiastic, so I thought, there's got to be a better way of doing this. And so let's sit down and write an algorithm that can automatically do this every time. And I failed for at least 5 years to get anything that was robust enough to be able to do what I wanted to do. And I went through hundreds of different approaches and probably did some of them wrong. And so that's why they didn't work. I noticed things that people are doing now that I'm pretty sure I tried that never worked. Well, it never worked for me. Anyway, but I did learn a lot about image processing. That wasn't certainly not my background. But it is important now that I know about image processing because a lot of the biomechanics research which is coming out is heavily focused on machine learning and machine vision type approaches. And so that's been awesome for me. And we did actually finally get an algorithm that did work as well. And we shared that to the community. And I think there's about 30 or 40 different labs across the world which use our software to track dynamic function in particular of muscle fibers during different tasks and muscle contractions. So, but as I say, it took at least 5 years of failures to get there.
But that just saved like so many PhD students and other researchers so many other hours and years.
My students would say no. They think it's created more work because now we just make more elaborate experiments, right? So now we just do more elaborate things. So there's just like 5 times as much to track. So yeah. So swings and roundabouts.
Well, thanks for sharing that with us. I think, a lot of people can relate to the fails, but I really find that particularly inspiring in terms of your perseverance and continuing to work on that. So that's awesome. Before we ask your last question, I'm wondering if you can share how people can learn more about you and follow your work. I know you're on Twitter if you want to share that or any other ways that would be good to to see your work.
Yeah.
And follow all your nerdy things.
Yes.
Yeah. So I'm on Twitter. I'm not very good at Twitter. I'm not very good at social media, but I do like to share people's stuff and occasionally say something. So you can follow me on at Glen Lichtwark. It's a fairly unique surname, so it should be fairly easy to find. It's Lichtwark. But yeah, as I say, and I've also got lots of students who are actually quite good at this, so they sort of hold my hand a little bit when I have to do something on social media. I don't mind it when people email me and ask me questions. It's really nice. Sometimes it creates really great, long-lasting collaborations. And sometimes it's just a matter of helping somebody out, and you can do that in an email or over a Zoom call, quick Zoom call or something similar. So I'm always happy to help out where I can.
Yeah, that's great. I always feel like those little times kind of help keep things going too. I feel like even if the rest of my day was maybe unproductive or didn't go as planned, like at least there's one part where I'm able to assist somebody else.
Yeah, it's actually one thing that I really love about Twitter, or more so than other social media platforms, I think, is that people do kind of, like in the biomechanics community in particular, as you know, people do try and help out where they can. It's generally constructive rather than destructive.
Yeah, that's true. I've actually been really fascinated with sometimes the very technical conversations that are had on Twitter, and people jumping in from all different perspectives and sharing research that we might not have seen otherwise. So it's been really cool.
And resources, I think, is something that I've noticed a lot lately. Obviously, you guys at Stanford and Scott has been very much a leader in being able to make biomechanics resources openly available. But there's so many more of these now than there was. And people like Luca Modenese, who's created like a resource GitHub page for everything that you might want to do about all the free resources basically in biomechanics. And those things are fantastic. And they just, as a biomechanics community, we've always tried to do that. So the BioMechL list server, for instance, was for a long time that tool that did that. And I think that's just shifted a little bit now because of how we do things now. The ISB in particular has always had code sharing and resource sharing, and it's now that it has moved to a much more sort of social media way. But I think it has been like that for a long time, but now it's just sort of exploded.
Yeah, definitely. And it's interesting to think how it will also shape the future of biomechanics. And so with that, we're also really interested in what you are most excited about for the future of biomechanics.
What am I most excited about? I think what I'm most excited about is that I've seen recently that there's been a shift away from trying to sort of describe everything at the population level and much more on the individual, and trying to understand individual differences a lot more. And that's only really possible because now it's easier to collect much bigger data sets, which can help inform those things. So, whether it be collecting more minimal data using wearables or using just basic video to try and look at specific biomechanical markers. And so I'll give a plug to your recent paper.
Thank you.
On this. But these types of things actually make it accessible to get bigger data sets and therefore drill down on the individual. I think that's what I'm most excited about because it's something that's been missing for a long time. And we've had, I'm sure that I will still be doing, or students of mine will still be doing studies on 10 to 20 people in the next 15, 20 years. But I think we're going to see much more big data type things coming out that people can really drill down into and therefore explain the individual, not just the whole group.
Yeah, that's going to be super powerful and super exciting for the future. Well, thank you so much, Glen. This has been so lovely, and it's been such a great conversation. I feel like you blew my mind with reframing crouch gait and cerebral palsy. Like I was thinking about that in the background for a long time, and how that might be an adaptation and actually lead to more functionality than.
I'm not saying that necessarily is it.
No, I know. But the perspective shifts. I feel like this whole conversation has been a lot of reframes, and it's just been really amazing to get to talk to you.
No worries. It's great to talk to you guys too as well.
Yeah, thank you. It was great to see you. And thanks for the great conversation.
So now for our favorite time in the episode. Just kidding. Every time is our favorite time in the episode. We are going to talk about research fails. And I thought Glen had a nice fail to share with us, and a great example of persevering through hard times and hard research.
Research fails. Yes, it does.
The fails I want to share today are actually not fails made by me necessarily, but they're made by tools that I rely on to help me.
Okay. Yeah, that's fine.
Okay, I feel like I should just explain it. So basically, there's two things that I do when I am, doing any kinds of writing. I like to have my computer read the writing back to me to make sure it sounds okay. And then obviously I use spell check to make sure things are spelled correctly. These are ways I review my work.
I didn't know you did that. I like that you have it read back to you.
You can have it read in whatever voice you want. So it's really fun. And I just don't, I'm a very visual person, but I think sometimes your brain can fill in things and then you miss them. But if you hear them, you don't miss them. So anyway, my long story short is that I was having my computer read an abstract back to me. And in the abstract, we talk about biomechanics and we talk about IMUs. And my computer pronounced them biomechanics and emus.
Biomechanics?
Biomechanics. And it just sounded like emus, like those birds with the long necks.
Animals,
I had just written, something about birds and biomechanics. It was great. And then spell check, I think just really had a kind of minor spasm or something because it tried to correct the word knee, Knee, to dog, like D-O-G.
Yep. That is not even close. I'm looking at my keyboard now to see if those letters are by each other, and they're not.
They're not. That was
confirmed. No,
and I loved it. So sometimes you have to check the things that check your work.
Yeah,
and that is the lesson that I learned from that.
Yeah, I have to work with the voice a lot with some of the work I do in consulting, where we type in feedback for people to do exercises correctly, and then it reads it out loud. And so a lot of times you have to spell things not correctly. Like if it was saying biomechanics, you'd just spell it like bio and then with a K or something crazy.
With a K,
so sometimes, you have to get creative with that. But I could see that being an issue, especially in science with more technical terms. So yeah, thanks for sharing that. No
problem. I always love sharing fails.
Yeah, I have a couple actually, because I had a couple of papers rejected. Oh well. But one of them I was confused because the feedback was actually really positive. And so that was something that hasn't happened before, where I read the reviews and I was like, oh, this must have been accepted. And then I was like, okay, well, that's confusing. But anyway.
Mixed messages. What's going on there?
Signals. Come on now. But learning a lot through that process as I'm just kind of new to this submitting papers. So if anything, it's a good thing, that I'm submitting the papers to have some failures. So
tab 2.
Two.
That's huge.
That's awesome. And then I'd say my other failure
the more the merrier.
Exactly. Then I'd say my other failure was yesterday. We went to the park to do a socially distanced yoga together for Hannah's birthday. And I shouted across the whole park, happy birthday. And then Hannah comes up to me and she was like, it's tomorrow. I was like, it's in my calendar for today. And so we're celebrating it today.
You're right. Actually, everything I've known about my life and my birthday is wrong. It actually was yesterday.
I'm sorry. It's in my calendar.
Your calendar
so
was correct.
I think you're confused.
So many things, May. And I remember you once saying that your goal was always to fail, so that even if you succeed, you failed at failing. So it sounds like you're doing all the right things.
If you try to fail and you fail, then you succeeded. Yeah. So
yeah, exactly.
Yeah, it's been however many years since we first said that, and I think it still holds true.
Still holds true.
Always aim to fail. But I did see a quote recently that said, failure is inevitable when you're pushing the limits of knowledge. And that was by astronomer Erica Hamden, who's an astrophysics professor at the University of Arizona, in her really awesome TED Talk. So I would suggest looking that up because she talks about failure in that. But it really resonated with me. I was like, that's very cool. And like, it's just a cool perspective to have, that we're pushing the limits of knowledge. And so we're bound to fail.
We're bound.
We're bound.
It's our destiny.
Exactly.
I think that sounds like something that should be a boom bite. And if you haven't checked it out, you should check out our brand new, as of 2021, Instagram account that has amazing inspirational and quotes and fun facts and just a lot of amazing boom.
Yeah. And if you want to share your boom bite or a bit of boom or something cool about biomechanics, you can add us at Biomechanics on Our Minds on Instagram. Or you can holler at us on Twitter at Biomechanics OOM. You can follow us on Facebook now at Biomechanics on Our Minds. And you can email us at biomechanicsonOurMinds@gmail.com. We also love to have ideas for new speakers. And if you want to host your own episode, that's also possible and something exciting that we really enjoy. So feel free to reach out to us.
We appreciate you so much for listening to this podcast. And we also have a lot of other people to thank. We'd like to thank the International Society of Biomechanics for their support.
We like to thank Peter Washington for all of the amazing music. And we'd like to thank Glen and everyone else who makes this podcast possible by being on Biomechanics Off Our Minds.
Boom, 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 boom.